Howdy, everyone. Hello. Hope you all are having a great day. I can see some traction. And here is my awesome partner, Perminder. Hi, Perminder. How are you doing?
Great.
All right. Pumped up to join the show? Another episode of Great Howdy Partner?
Sure. I've been doing this from last 2 years now. Means we have a wonderful partners from all over the world. And today we will be talking with one French partner.
Yes, absolutely. Looking forward to. And today's topic is of my let's take off my personal bias here, but it's so interesting, and I'm going to keep the suspense on going. But everybody knows Howdy Partner Show, what it is about, and how we bring our great, awesome partners to showcase their even better solutions and products, doing advancing in technology. And as we speak of that, today's guest is ColibriTD, and they are a Paris-based company in advancing in quantum computing technology. Founded in 2019, and they specialize in developing hardware-agnostic quantum computing solutions aimed at making quantum technologies accessible to all the enterprises across variable industries like aerospace, automotive, healthcare, and many more as we speak. So, do you have anything more to add here, Perminder, before I bring on my great, awesome guests?
Yeah, let's bring the guests on. We don't want to make them wait. It's all about the partners and our customers. And I will share my insight as we go along. Let's
Sure,
invite them.
absolutely. I have two great folks here, Hamza and Henri, who are the pioneers of the R&D research and development team for this quantum computing technology. So let me welcome them on stage. Hello, Hamza and Henri.
Hello,
Hello, everyone.
hello, everyone.
So yeah, we would like, and our audience and myself, Perminder, we all would like to hear a detailed introduction about you all, what you have done, the journey, everything. And we will be bugging you with questions. So yeah, go ahead. Whoever wants to start.
Perfect. Go ahead, Hamza.
Okay. Hello, everyone. Thank you for inviting us in this show. We are very happy to discuss with you and to present to everyone on Twitch our activity and research. I'm Hamza Jaffali. Um, I have a background in computer science. Did an engineer degree in France, east of France, a small city called Belfort. It's close to Switzerland and Germany, actually. And I was studying 3D simulations, uh, virtual reality, video games, and stuff like this. And then during my study, I met a teacher who started to be interested also in quantum computing. And then we started to discuss, discover, and even do research at that time. And then he proposed me to continue on a PhD with him. So that's how I really get into the field. And so my subject of the PhD was to study quantum algorithms like Grover and Shor, and to study the effect of quantum entanglement, which is a typical quantum phenomenon, and how it can help accelerate or what types of entanglement appear in those algorithms. So it was a lot of algebraic geometry, mathematical objects to manipulate, and a bit of machine learning. And then I teach a bit of computer science at university, and then I had the opportunity to join ColibriTD. The startup was just starting the R&D activity on quantum, so I was one of the first to be able to contribute in this journey. So nice to meet you all.
That's
I think it's
fantastic
sufficient.
introduction, Hamza. I was about to bug you to tell me the story that what inspired you, and you said it fantastically. So thank you. And Henry, I would again do not mind to hear your story about.
Yeah. So I was always very interested in mathematics, and like the more theoretical something is, the more interesting it is for me. And so in this mindset, I had a very similar background as Hamza, where I did an engineering school in computer science. Computer science is basically the way to do math but earn money while doing it. And at the end of this, I still had some regret. I didn't want to dive into the industry right away, and instead I searched for every opportunity to do a PhD, in particular a PhD in quantum computing, because like a few months earlier, I fell into a rabbit hole of quantum computing online, read a ton of books, papers, and watched videos and so on. I was super interested. And so very fortunately, I managed to find a PhD last minute. And the PhD was about using quantum properties to formally prove quantum programs. So we can dissect a bit what all this means. Quantum properties, it's like quantum entanglement, contextuality, things like this. So it's a way to characterize a quantum system. And to formally prove a program means basically to split your program, like the instructions of your programs, as mathematical bricks, and then to try to assemble those bricks as a mathematical proof, like the same way you would prove Pythagoras theorem or Thales theorem. You can prove a program, and this is something which is done already for classical computing, like for the autopilot of an airplane, things that are very critical. You would try to formally prove them. Of course, you would only prove those vital parts of a program, because it's something that is quite hard to do, because you have to be very comprehensive. It has to like take as possible input all the possible inputs of your system. And so the goal was, okay, we know how to do this for classical. Can we transfer this knowledge to quantum? And I had the big luck of being able to write my first paper with Hamza, in fact, during my PhD. He was a bit ahead of me. He was already in second or third year, something like this. And so thanks to him, I also joined Colibri at the end of my PhD, where he was already.
Nice.
Wonderful. That's wonderful. Yeah, quite a story. Excuse my lack of knowledge here about this, but I do watch a lot of videos and theories about the quantum entanglement aspect, what Hamza just mentioned, and then Henri, you repeated. So, and then, yeah, there is I don't know, I'm sure you all know about the Fern, the collider, and everything. So, yeah, if you guys are very lucky to start in that aspect. Yeah. Let me know if you are looking for a volunteer who you want to shift it to a parallel universe. I am up for it. I would love to take that on. So, but yeah, quantum computing is a hot topic, gentlemen. So, but it is often viewed as so futuristic. And I also wanted to how ColibriTD will make quantum computing relevant to the industries today, besides the other volunteering subject I talked about. So yeah, let's emphasize on that how would it relate to different industries.
That's a very interesting point. So there are basically two parts for in general computing systems. You have the hardware, like on your computer, it's your CPU, your RAM, and so on. And then you have to write some software on top of it. We have, in the quantum ecosystem, we have a lot of hardware providers, we call them. So people who build the equivalent of the CPU, we call it the QPU, quantum processing unit. And we start to have a lot of different sources of QPUs. So even just in France, we have Pascal, we have Candela, we have, I could go on and on. And then in the US, you have maybe the big actors. So AWS, what the role of AWS, from my understanding, is to make a platform where you can access all the QPUs that are provided. And then you have other independent providers, such as Google make one of their QPUs, but I think it's not directly accessible to the public yet. IBM makes one, and so on and so forth. And so, okay, we have the hardware, let's say, and it's relatively accessible nowadays, but we don't really have a software to put on top of it, in the sense that, okay, maybe we have a software to access the hardware, but we don't really have, let's say, the bricks that are necessary to easily interact with it. What do I mean by easily interact with it? I mean that someone that doesn't know quantum computing today cannot use a quantum computer. It's completely impossible. And so our goal at Colibri is to make that something that is in the realm of possibility. So our goal is to write quantum programs that can be used by non-quantum engineers. And in particular, we focus on industrial use cases, because today quantum delivers the biggest promises in very big problems, and very big problems can often be found in industrial workplaces. So, for example, it would be something like flame simulation or combustion, something like this, for the creating an engine of a car or a plane. It would be material deformation, things like this. So such simulation are very complicated to do for a classical computer, and our hope, and you will see later on in the presentation, that in fact it's something that we managed to realize already, is that it's easier to do on the quantum computer.
Oh, absolutely.
Yeah. And there is an analogy which I often give, as we are in an era of how we were like in classical computer like 30, 40 years ago, right? And they were a programming language, Fortran or COBOL, and they were very hard to code, right? Like it was like a very special skill. Now, with the advent of Java, .NET, and then the Python in the classical world, the programming became a little bit easy, because what we did was like we created abstraction layer. And by creating an abstraction layer, sometimes it is easy for the programmers to interact with the hardware and the databases behind it, right? They will write once a package or a plugin, and they target the multiple databases like that, right? So same analogy, if you use it here, so companies like ColibriTD are building that programmatic layer, right? So that you can write once, and then with the minimum config changes, you can go to either of the hardware. Now I'm saying it at very high level, but yes, under the hood, there's a lot of work goes behind. But then as a user, my user experience in accessing those hardware should be very, very abstracted, right? In a way, so that I don't spend time in writing like tons and tons of code, rather than I just write a little bit of code in using the SDK, and then I'm using those system. So Hamza, I don't know if you want to add.
Yeah, and yeah, to mention AWS and why we love to work with AWS is that for us as quantum developers, it's really a simplified platform to access all of these computers, and to do complicated quantum computation. Sometimes you have hybrid jobs, sometimes you need to control, to monitor everything, different types of jobs. Sometimes you want to try on a simulator, then go to this machine, etc. This is very useful for us, as we want to come then on top of AWS platform to provide those algorithms that will be directly linked to the industrial use cases. And for us, being able to describe those algorithms and to run them very easily on the AWS platform, this is something it's very important for us for productivity, and being able at the end to show the whole pipeline from the industrial user bringing his use case, some inputs to the algorithm, then the algorithm bringing some requests and jobs to the AWS platform, running on the quantum computer, and then all the way back with the simple interpretation of the results. So for the user, everything is transparent. This is the spirit of what we try to achieve at Colibri, and we're very happy to collaborate with AWS for that.
Great. Yeah. So can you tell us something about the company? I mean, I know most of the stuff, but for the benefit of our audience, like Laurent, and then how it all came together and when he started working.
Yeah. So I think the company was founded in 2019 by Dr. Laurent Guiraud, who was a former of AWS, Google, also Oracle. So he was always ahead in the project and have innovative vision of the project, and was also founded by the CEO Hassan Gouchil, who is more on the business side, 20 years plus of experience of business, and they went together. They have quite complementary profiles, and so together they started in 19 started active so Colibri. So at the beginning, it was more consultant in big data. So they want to start an activity they were confident in to have some to gain some speed and some money so they can reinvest on the R&D part. And then in 2021, we started the R&D activity of Colibri with me and my colleague Jonas at the beginning. And then people started to join the journey. And now we are more than 12 researchers with Hassan and Laurent. So we are 14 almost. We are based in Paris and we're happy to be based at Station F. So it's a big campus of startups with almost 1,000 startups. We have also there AWS that is physically present, so it's very helpful for some direct support. And we are located at what we call the home of quantum, la maison du quantique in French. So we have a bunch of startups that are working at the same place. So we want to have some emulation, some discussion, some collaboration going on in this house. So we are very happy to be located at this place. So it helps us collaborate together. I don't know if Henri want to add something.
No, I think you said the most of it. Indeed, I really appreciate this Maison du Quantique thing where we can like go to the next desk and just ask someone, okay, but how does this work on your computer? Could I use it? And it's very, very interesting. Yeah.
Mm-hmm. And this center, you said, like it's like a public-private partnership from the French government.
So the Station F, it's fully private.
Okay.
But there is some public money laying around, let's say. But specifically, Les Maisons du Quantique, I think it's kind of public subsidized association, something like this. And so, but it's all the companies inside are fully private.
Mm-hmm. Gotcha.
So yeah, I mean, let's see more into what your product is.
Yeah.
Okay, we can cue a short presentation, and then we will go into some real-world demonstration.
Absolutely.
I think you have my screen available, maybe.
Let me bring it on. I think this is, you have to go ahead and share it, Henri. I think I'm sharing, so this is not the one.
Because I see mine has
There
been shared already, but I can try again. Yeah, perfect.
Mm-hmm.
Okay. So, I mean, in our short introduction, we've already said some of this. But indeed, so the reason why we have Colibri and why we think it's an important piece of the puzzle, of the quantum computing puzzle, is that we notice that in general, in quantum computing, nowadays we don't have ways for non-quantum experts to do things. So we don't have the plug-and-play experience where you download a program on your computer and you can run it and do your simulation and then go on your merry way. And this goes a bit hand in hand with the fact that if you want to do something on the quantum computer, you have to be really an expert of the topic. It's a very exclusive skill that you need to have. So we want to free a bit ourselves from this logic and to allow our user to use the power of quantum without needing to know the deep knowledge of quantum. And then there is also another potential problem is that we have a lot of hardware providers. And in fact, once again, our clients cannot know every hardware provider and which hardware provider would be good for which specific problem. And so we want to facilitate that choice and even to automatize it. Let's say, if you have this type of problem, then we know that this type of hardware is good for you. And so this is the reason why we have in Colibri the good elements to solve these problems. So our solution should be integrated. It shouldn't disrupt the user workflow. It should be user-friendly in the sense that the user knowing his tool will not be lost at all in using our products. And we have some powerful algorithms that we can go in details later on that allow us to tackle efficiently the problem that we promise to solve. So we have for now 3 main use cases that we promise to solve. So I told you a bit earlier that we were focusing on industry, and so in particular here we have 3 verticals of the industry. We have combustion, fluid dynamics, and material deformation. But in fact, you will see that our solver can be generalized much further. So I can tell you a bit more about the context in which we do the work. We already have some clients that we are working with hand in hand to make sure that the problem we are solving are indeed solving for someone and not just like theoretical problems that have no application. And we already have hardware partners and academic partners that help us make a cohesive, let's say, a cohesive system that is theoretically sound and that is built on real bricks on a real hardware that it's not theoretical or anything. It's something that really works. So our algorithm, we embed it in a platform that we call Quick for a quantum innovating computing kit. And Quick is composed of 3 main elements. Our algorithm, that we'll go into detail later on, which communicates with a library that allows us to interact with the hardwares. So if we consider a certain user using his tool of predilection, he will only interact with the front end of our platform, and then in the back end, our algorithm will run, calling our library that already exists. And this library, once again, we will go into detail later on, but this library is open source and available for everyone who wants to use it.
Yeah, let me go ahead and those links which you have given for the GitLab, right?
Mm-hmm.
Absolutely.
It's a GitHub, but
yes.
Yeah, sure.
Putting this in the chat for our audience. Please try it out. This is open source. And sorry about that. Carry on, Henri.
Yeah, and we love any feedback for potential users. We are this library. We are working on it with students, with other partners, and we love to exchange about it because it's by mixing ideas that we manage to really solve the problem and find new point of views. Okay, and so this library then allows us to interact with the hardwares, and then the solution comes back from the hardware through the library, is parsed by our algorithm, and then returns to the user in a user-friendly way, let's say. Okay, so our algorithm, we call it the Hybrid Differential Equation Solver, HDES, and it's an algorithm that solves differential equations, and in particular, partial differential equations. And it's a quantum classical algorithm. In particular, we call it a VQA for a variable quantum algorithm. I'm sorry, I'm throwing a ton of words. If it's too much, do not hesitate to tell me to tone it down a little bit. But so a variable quantum algorithm means that you have an algorithm, so a quantum algorithm in which you have some parameters, and you can tweak those parameters using a classical optimizer. So that's why we have the quantum quantum classical algorithm, because you have your quantum algorithm, which is controlled by a classical algorithm on top of it. And that's also why we call it hybrid, because it's a mix of the two, right? And then the theory behind it on how we model the equations, it's called a spectral methods. So for those who did some math in their curriculum, they might be familiar with it. A spectral method is just saying that your function is represented by a specter of the function by like when you do a Fourier transform of your function, you have a certain representation of your function in terms of coefficient in front of other function. We don't really need to understand exactly what these terms means, but it's a way to represent in a quite minimal amount of memory, very dense information. And the strong point of our algorithm is that it requires a low number of qubits. So qubits are the elementary bricks of information in a quantum computer. And the problem nowadays for quantum computers is that you have finite amount of resources. And so if you need too many qubits, probably you can't find a quantum computer to realize your problem. So this low number of qubits, basically the equivalent for a classical computer would be it requires a small amount of RAM, of random access memory. You don't need a lot of memory in your computer. Then the quantum equivalent is you don't need a lot of qubits. And with this low number of qubits, you can still reach a high precision on your solution.
So, Henri, with this HDES mechanism you're explaining here, is it a form of how this that data will be showing the workflows and algorithmic principles behind the scenes?
Yeah. So HDES is here in our first brick
Okay.
of our platform. It's the name that we have for our algorithm, and it's allow us to solve the equation that our user need to be solved.
Yeah.
Okay.
Yeah, and there is a little bit of importance to the word here, like hybrid, right? Like hybrid. Why does it called hybrid? So this is another analogy which I often use to explain this in a very lightweight way. Like if you have machine learning, right, and you use the classical computer and then you use the GPU, right? The GPU is where you do a lot of training and inference, right? And then most of the evaluation of the parameters, the loss function, and all happen on the classical computer. So you just replace that part of the GPU with the quantum processor unit. That is what it makes a hybrid, because classical and then the quantum processors work together. You prepare the data quantum for the quantum computer on the classical and feed it, and then the forward network, the neural network is sort of and the quantum, right? But the neural network is designed in a different way, not like classical neural network. But the cost function and then the adjusting of the parameters then again happen on the classical. So that is why like there's a little bit of like involvement of classical resource and the quantum resource, and that's the word why we use hybrid here.
Yeah, and it's a very good parallel for two reasons. First, indeed, we have this. So for machine learning, you would have your CPU controlling your GPU. And for a quantum hybrid job, you would have your CPU controlling your QPU. So we have this parallel, but also for machine learning, you have your neural network, let's say, with parameters inside, and when you teach your model, what you do is that you tweak your parameter to try to have a realistic view of the world, let's say. And it's actually the same for the quantum system, where you have a quantum circuit with some parameters, and you will tweak the parameters of your quantum circuit to try to be as faithful as possible in our case, to the equation that we are trying to model. But in other cases, it will be to be faithful to the thing that you're trying to represent.
So right now, as a hybrid loop, what's happening here is the classical data is meeting the quantum aspect or the solver, right? So it's taking that data, kind of translating and then processing it, right?
Yeah.
Okay.
So as an input, we give the partial differential equation. That's what PDE stands for. And then we encode it in a certain way. We can check later on how we encode it exactly. This is a bit mathy, but it's not too bad. And then once it's encoded to be used by the quantum circuit, we build the circuit, we run it, we extract some values from it, and then we do the evaluation of the differential equation from these values that come from the quantum circuit. And given the differential equation, we see, okay, was the solution good or bad? If it was bad, we tweak the parameter to try to improve it. And that's what happens here. And in the end, once we find a loss function which is low enough, then we can return the output to the user and say, okay, we finished optimizing the circuit, and the answer of your question is this.
Makes sense.
So we can do a demo. Let me change the screen I'm sharing. So this.
While Henry's changing the screens, let me tell my audience, please don't forget to give us a feedback on the survey I have just shared. I'll go ahead and share that link in a moment again, and let us know your great, valuable feedback. How are we doing? What else would you like to hear and watch on this stream?
Okay. So I think my screen is ready to be shared again.
Okay, let me see.
Tell me when you do see it.
Yeah, great.
It's okay?
Yeah, it's okay.
Interesting.
Okay, so this is our platform. Of course, for now, the greatest amount of effort that was put into it was at the algorithm level. So don't pay too much attention to the details, the aesthetical details of it, let's say. But you might recall that I talked about 3 use cases: metal deformation, fluid dynamics, and combustion. So here are 3 use cases, and then we have more use cases that we plan to tackle.
And these use cases can belong to any very more specific industries, Henri, or
yeah. So we have some use cases that we already know that our solver will tackle well, and in this case, it means that it will require not too much effort from our part to add to our solver. And then we also have some conversation with other verticals that are interested in quantum and would like us to improve our solver to solve also their problems. So it's always a mix of opportunity. We know that our solver will work, and so we put it directly, and partnership, where someone interested in the solver might say, okay, I'm willing to put some effort to work with you to try to make it work with your solver.
CFD is very relevant for the automotive, right? If you want to know like which specific industry.
Yeah.
And there is a classical way to do this CFD, right? And we have a HPC solution on AWS for CFD, but then the promise is like at certain point, right? Certain, that point would be probably few years, right? We don't know when, but it will have advantage over the classical in terms of, reaching that approximated solution in very fast, exponential way, right? So that is the promise in the future.
I mean, all of these use cases have already existing classical solution, but for big problems are potentially very hard to solve. Like if we take the example of CFD, if you want to be super precise, you would have to do simulation at the molecular level, maybe something like this. You have to use finite methods, simplifications. And so if we can find more powerful methods, it means that potentially we can build more efficient cars, more efficient planes. So yeah, it's the promises are very big.
And also, let me specify this for the audience. Quick is not the word which you all are thinking for, and it stands for Quantum Innovative Computing Kit. Now, only for those who would not know. Just wanted to throw it out there.
Yeah, thanks.
Thanks.
Okay, so let's say that we are picking one of the equations. So you can see that this is really aimed at the engineers. Well, for now, we are trying to involve engineering in our process. So this is one of the ways to solve fluid dynamics problems. So we pick a set of equations. Okay, here we have the equations display. We can pick in which dimension we want it to be solved. We can pick a few other properties that will simplify or not the equations. And then once we are happy with the parameters that we set, we launch the simulation. And then we have this UI. So the goal of this UI is really to show the comparison to classical, because this UI has for the main goal of the UI is to onboard people to our platform, and so we will it has to be familiar to the person who solved CFD. So okay, the flow at this point in space and time is of this amount, things like this. We have a comparison to classical, where you can see, so attempt OA, so attempt is the quantum solution, and target is the classical pre-computed solution. And so here you can see that the two overlap exactly, which is a good sign. Yeah, I think that's it for this specific demonstration.
And so here, what happened when Henri launched the simulation is that in the back, you had some API calls to the algorithm, and then quantum computers, simulators, and then all the way back, and you have this nice display of the results. So for the user, it was completely transparent, and this is really the goal that we aim for.
And those two attempt and the other process you integrated were also from the quantum computing aspect, right? To process the data, right? In the time of space when you were showing out the UI.
Yes.
Okay.
So the quantum computer only extract the numbers for you, and then after, to display them in a user-friendly way, it's just reorganizing the data and making it all fit on your screen.
So how have you leveraged AWS Bracket or services into this product of yours? Like what?
So as maybe Hamza, you want to answer?
Yes. I think we'll show it also later in the more technical hands-on code simulation. But here, the algorithm is described in a Python library, but at some point it has to run on some platform. And so here we come on top of AWS. At some point we submit this algorithm to the platform, and then we have the choice to run it on IQM, on Qera, or on IonQ, or Rigetti, and also on the platform. But we didn't show it, but the user also could have the choice to experiment on which quantum computer he wants to solve, and maybe this one is more suited or not. And at some point we will also make an automatic choice for him. So the fact that AWS give us simulators, so first we can validate the algorithm, but also we can go further, we can run on quantum computers, and we have the choice of several platforms. And so here, this is what's important in this whole pipeline, is that at the end you have to run somewhere, and this is allowed by having access to AWS resources. So yeah, this is very important for us, and we will show later some simulation directly done with using AWS Bracket as a backend, and
Great.
so
Yeah, I thought so. Yeah, actually, somebody was asking as a question like, "What is it?" So, just for the sake of audience's question, it's AWS Bracket is a managed service by Amazon Web Services, and that allows users to explore and experiment with the same quantum computing technology what Hamza and Henri are explaining is here, and it provides access to those hardware from different providers and some even classical simulators. Like it lets users develop, test, and run quantum algorithms using popular frameworks without having it to bought it and just to experiment it on the main platform. So let's move ahead, and we will talk about the use cases, like mainly used in research and development. But yeah, we'll talk more into this. Go ahead, folks.
I mean, even if we want to go in a bit into the details, so today, quantum, quite similarly to machine learning, is very much relying on Python as a programming language. And so all our algorithms are in Python. Our library also is in Python, MPQP. And so Bracket is also a Python library that allows you to access the quantum computers. And it's, yeah, as Hamza said, it's very useful with a single library to be able to access several hardware behind. So yeah.
Yeah, I mean, and then of course the web front which you guys showed, right? That runs on a classical, and I'm sure you're using some open source framework, and then I am guessing like that was a matplot graph, right?
Yeah.
Like that all are classical, right? That's what I said. Like hybrid means classical data, prep data showing, and then the quantum for the quantum part, right? So it's a little bit of hybrid going on. The solution is built on AWS. Using the Bracket, which is a quantum computing service, but there is tons of other services which is being also used. So it's like a first class, sort of like a SaaS application.
Mm-hmm, mm-hmm. Yeah, exactly. Yeah, we have the containers, we have the database, we have the our user base. We are using Cognito to connect our users, things like this. All the usual Amazon AWS services. I think, Sarah, you can share my screen again. I switched back to the presentation. So, okay, we can go a bit into the details about the spectral methods. If at any point it becomes too detailed, Sarah or anyone else, don't hesitate to interrupt me, and we can go at any point back to some demonstration. So, maybe a small note on spectral methods. I went very quickly earlier, but here is a way to represent your function using spectral methods. So you take your set of function, which should be orthogonal. So the function being orthogonal means that basically they shouldn't span the space of function all in the same direction. You want to have a very homogeneous. It's very hand-wavy math at the moment, but for the sake of explanation, you should try to span your space of function as homogeneously as possible, and then you can build any function as a sum of those linear sum of those orthogonal functions. So an example of those orthogonal functions is the Chebyshev polynomials. So here we have a formula for our Chebyshev polynomial. The exact formula doesn't necessarily matter. The important point is that we have a relatively easy way to implement them. So you see it's basic trigonometry. And so these functions, parameterized by k, are a way to represent any function. Then, how do we encode the function using this? So here we are starting the real quantum scientist job, where we build a circuit. So here, each wire here, each horizontal wire represents a qubit. So it's equivalent to a wire in your processor. And then you have those bricks, which are rotation gates. So it acts on the qubit. It will modify the qubit in some way. You have those vertical wires that represent interaction between your qubits. It's a way to force the qubit to do something. And we talked about entanglement earlier on. this is maybe the most important gate that allows us to create entanglement. You cannot have untangled qubits without those 2 qubit gates. And then assembling all this in this manner, you have a circuit parameterized by some angles. So here you see theta 0, theta 1, and so on, up to 9. So here we have 9 angles parameterizing our circuit. And this means that for a given state, so a state is a way to represent how your quantum processor is at some point in time. Okay, so at the beginning we say all the qubits are equal to 0. We initialize all the qubits and then we modify them in some way and they become something else. So at the beginning the state was 0 and then we modify them with all those operations and they become something else. So we represent the state by this ket representation. And here this ket representation is indexed by theta because theta is the angle. So if you change theta, you will change the output state of your circuit, right? And then you can say, okay, if you remember earlier on, I said that any function could be represented by a sum of orthogonal functions. Here, our orthogonal functions are the Chebyshev polynomials. And here we notice that, okay, there is something a bit different compared to what I said. Maybe I can go back a little to the previous slide. Here, I only had our function, pk, and some parameters. Here, the difference is that we have here Chebyshev 0, Chebyshev 1, and then again Chebyshev 0, Chebyshev 1. This is just because in order to be able to represent also negative function, we add basically the same terms second time with a minus.
So this means that if you go back to the previous state, Henri, that was the standard Chebyshev polynomial, and this is a two qubit means like in a positive and a negative aspect of it, right? And these are all pre-embedded. If I am as a user, go ahead and leverage your GitLab link, we can do a demo process of these, right?
Yeah, so these Chebyshev polynomials are, of course, not at all, I mean, of course, for me, not at all displayed to the user because it's how we encode the function behind in our algorithm.
Yeah, I see it.
But the user only needs to give in the equation, right?
Makes sense, yeah. Less complicated.
And so here at the end, we can find indeed, as I said, the encoding of the function with our Chebyshev polynomials and some coefficients. And this, in fact, we see, okay, we have 4 terms. How could I encode it in a quantum manner? Okay, let's go a bit faster. I can represent it as an observable. An observable is, in quantum terms, it means it's a way to do a measure at the end of your circuit. So, because, okay, you need to measure your circuit because quantum information is not accessible right away. You cannot look at a quantum wire and know if it's on or off, unlike a classical computer where if there is a voltage, it's on. If there is no voltage, it's off. For quantum computers, to access the information, it's a bit more involved. So you use those operators, which are represented by matrices, and that we call observables. And if you put those Chebyshev terms on your observable, then you notice that for a given state, you can just measure your state by this Chebyshev special observable, and it will give you the function returned as the solution.
And what do you mean by circuit in this perspective, in this scenario?
So circuit is this part here on the top right, the qubits with the gates operating on them. So it takes in an input state, usually 0. It modifies the state in some way, and then you have a certain output state.
Got it.
And so then at the end of your circuit, you do the measure, and the expectation value of your measure is a certain the function that you expected. So all this to say that we have a very compact way to find the value of the function for a given circuit. So a single execution of the circuit with the observable will yield the value of the function. This is very powerful because usually for a classical computer, you would need, for example, if your function is evaluated by some complicated formula, let's say, you would need to do all the operations one by one. Here, in a given execution of your circuit, you have your value of your function. And it's even more interesting because if you need to have the derivative of a function, so remember we are talking about differential equations. So differential equations means an equation based on the value of a function and the value of the derivative of the function. If you need to access the derivative of the function, then you can just replace your Chebyshev polynomial by the derivative of the Chebyshev polynomial, and it's all the same. And so here again, what it means is that for the same circuit, you just swap the observable for a slightly different one, and then you have the value of your derivative. So this will mean later on that we can do some even more complex operations in a single step, which is very interesting. Okay, this is basically a repeat of what we said earlier about variable quantum algorithms. We have a certain state that we prepare at the beginning. We have a circuit that modifies our state, which depends on theta. And then the output is the value of the function in your differential equation. You check, okay, is this value of the function matching what we want for our differential equation? If so, then we can just exit the algorithm. If it's not the case, then we need to update the angles and repeat. So we have a few basic ingredients. We have the cost function, which is the part that says we are close to our solution or far from it. We have the ansatz, which is a name for the quantum circuit in the middle. And we have the classical optimizer, which is the classical part of our hybrid algorithm. So when I talked about the cost function, here we can check into more details. Maybe we don't need to go into the specifics of the equation, but just see that there is a part inherent to the differential equation itself, and then another part inherent to the boundary condition. So the boundary conditions means that, let's say that you're trying to solve a differential equation representing something in space, but you know that on the right wall of your container in which you try to solve an equation, the condition should respect something. So for instance, I don't know, you're trying to heat up a volume of air, okay? So you have a closed container containing more air, and you heat it from the right wall. Then you know that you put the temperature on this right wall to a certain temperature, like, I don't know, 200 degrees Fahrenheit. Then you know that the temperature here will always be 200 degrees Fahrenheit, whatever the temperature in the rest of the container. So this is a boundary condition. And any type of equation will have some boundary conditions. So your cost function should always have a part based on the differential equation and a part based on the boundary condition. And both of these parts can be encoded in our circuit and observable.
Henri, can you define the MSCs and DEs as well?
Oh yeah, sorry. So DEs stands for differential equations. PDEs is just the partial differential equations. And then MSE is the mean squared error.
Oh, I see.
So it's a way to evaluate how far you are for the real solution.
From the yes, absolutely makes sense.
Yeah, I'm very sorry. I'm so used to our jargon that I don't even see it anymore. Okay, so as I said, we have a few verticals. So now I can show you some example of what the differential equation can be for each of those verticals, for each of those use cases. So for combustion, we have a set of three equations with some parameters, some constants. And so we are trying to solve in many dimensions, specifically, we have to solve, I think, for time and space in this case. And the complicated thing for combustion is that it's highly chaotic. So chaotic for a differential equation means that it's very sensitive to initial state. If you have a flame and you start it with some wind on the side, it will be very different than if you don't have wind at all. An example of chaotic systems outside of this context is, for example, the double pendulum. If you have a single point and you have a pendulum coming out of this single point, and then you attach a second pendulum out of this point, if you start the pendulum twice from almost the same condition, they don't do at all the same drawings. You can have a look after that on YouTube. It's very mesmerizing. It's a very interesting system. In general, chaotic systems are very entertaining to watch. And
yes,
so, yeah.
Here is the title or a search or a link here. We will be more than happy to share it with our audience. And one of their audience's question is here. Sorry to interrupt, Henri, but they want to know that can you solve any type of differential equation with this algorithm, which you just talked about?
So nowadays, in classical, there is no way to solve any differential equation. It's something that just doesn't exist. And so there is no way to analytically solve them. And even numerically solve them is quite difficult. And our solver, it's quite general. It's not able to solve any type of equations, but we are actively working on making it work on more and more differential equations. But solving differential equations in general, even like for classical computers, it's something which is very, very tricky, and it requires you to have very specific knowledge because you have very, very different methods to solve differential equations, and depending on the differential equations, some method will work, other won't. So yeah, it's a whole field of research. Okay, the other use case is fluid dynamics. Here you see that we only have one equation, but don't let that fool you because this equation is multidimensional. So in fact, hidden behind it, if you're in 3 dimensions, this means that we have 3 equations. A simplification of this equation is the Berger equation, as you see here. So it depends on x and t. And we have some interesting results that we can see just after. Maybe I can add another note on Navier-Stokes. Those who did like climate modeling and things like this will recognize this name because Navier-Stokes is the primary equations used for climate modeling. It's used also for like wing simulation and things like this. So it's really a master equations hidden behind a lot of things. And so our results are here. So you can see it's quite similar to what I showed you online in the sense that as it's a tool for now, mostly for engineers, It's really oriented at graphs, showing, okay, are the graphs good? Is there error in the graph? Things like this. And so here you can see a solution of a specific version of the equation with some specific boundary conditions. Yeah, I don't think there is much more to say, except if people have questions.
Yeah, Henry, one question. Like previous slide, you said like simulating the traffic flow. So in layman's term, there is a mathematical way to do that, right? I'm sure you can explain. If we have to explain this to very like a 5-year-old kid, right? So there is a traffic, there is a car, there are roads. How you come up with the equation for that, and then how you solve this using your library, if you can.
So it's very empirical. What you would do, because for fluid simulation, you have some properties of your fluid. You have things like the viscosity of the fluid. And so when you observe traffic flow, depending on the condition, you can draw the parallel between your traffic flow and the simulation of a fluid. So say, okay, this is very viscous, not very viscous. Is it sticking a lot for a fluid? Is it sticking a lot to the edge of your container? So if you have water in a pipe, for example, the layer closer to the edge of the pipe will flow slower. And this would tend to be the case also for traffic. Like the lanes closer to the edge will go slower than the lanes in the middle. And you can even generalize that to human flow. Like if you have big crowds and see how the big crowds are moving, it could be seen also as some way of flowing. So yeah, this is very generic, but
great.
Each of these applications here are basically a different way to simplify the Navier-Stokes equations to some way that is more useful.
Great. And then once you have a better model of this traffic flow, then it will certainly help the urban planning and then the infrastructure set up by the local municipality and all. Okay, great.
Yes. Okay, and then our last use case that we tackled, which in fact was the first one, as a fun fact, what made us go into this differential equations thing is that there was a BMW challenge. So as you know, in Europe and specifically close to Germany, cars is a big thing, and so BMW organized a challenge for quantum companies to try to solve some problems. And the problems that Colibri chose was material deformation. And so the goal was to try to solve material deformation using a quantum computer. This was in 20... Yeah, go ahead.
21, yes. And actually, Adules was a partner of this challenge, and it was the first time that we had to work with Bracket, implement our first version of the algorithm, and run online hybrid notebooks on IonQ, etc. So it was so historically we all started with PDEs and AWS. So it's funny that we come back to it right now.
Yeah, full circle. This was in 2019, right?
Yeah.
Yeah, in 2021. Yeah, 2021.
21. Yeah. 2019 was the paper.
One of the audience is interested to ask, like, did you solve any equation on real hardware? So I think this is the best time to ask.
So this is what we are busy with it right now. Yeah. So that's why we want also to work closer with hardware providers, because okay, our algorithm require low number of qubits, but if we start to go to complicated case, still we will need around 50 or 100 qubits to with stacking those equations and circuits, etc. So yeah, we started right now to first we validate our algorithm on the simulator. Then we use noise models of the simulator to validate under noise. So this is also present in brackets, and maybe we will show at the end in the MPQP demo. And today we try to run on real hardware, and this is the joint goal with AWS, is to show that we can solve real use cases on real hardware with today's quantum computers. So this is the main effort of our R&D team nowadays, and we hope to have a result soon, so we can publish and then show to the community that something can be done in this sector of industrial simulation with real quantum hardware.
I'm curious to know that those awesome results we're looking forward to have soon would be also shared on the GitLab. All right.
Yeah, I mean, the solving on real hardware has several very important barriers. I think we will talk about them a bit later on, but one of them is the fact that to have access, so there are not that many quantum computers that are operating that you can use today. So
True.
I said that there was a lot of providers, 80 plus, but in fact, each of these providers has maybe one computer working, most of them. And a lot of researchers are trying to use them for their research. So in fact, the queue to access a given quantum computer can be quite long. And so this is one of the limits to try to run something on a quantum computer, especially for VQA. So you might have understand by now that the VQA, you have this back and forth between quantum and classical. And in this back and forth, it means that very often you need to have an access to the quantum computer. And if you don't have a specific way to maybe, I don't know, reserve it, then you have to do the queue each time. Do the queue for to run your quantum part, and then do your classical part, then wait for the queue again. And so this can take a very long time. There are solutions in Bracket, in Qiskit, and so on. Some solutions work better than others, but
I mean, we were kind of like trying to nail this problem. So that is the reason we released at last reInvent, our flagship, the AWS event, the direct, the Bracket direct. So where you can actually go and reserve the time, right? So because it's quantum computer a scarce resource, everyone wants to run, every researcher wants to run, but then as a researcher, if you need a time, a day when you are absolutely sure you will run it and you know that you will need 2 hours, you can actually go in advance and book it. But still then, some of these resources, are considered scarce because some of those resources are just for, available online for a few hours, right? And then that is the nature of where we are in terms of like technology. But hopefully it will improve, and that improvement we have seen like this week itself, we released like one of the QPU from INQ, the Forte, right? We increased the time to 15 hours, which is good. Now we'll see like, okay, 15 hours is not that much, but we're talking about quantum, not the classical computer, right? So this is good for us. If you ask me, like, yes, right now you can go to the Amazon Bracket and reserve, or you can get at least 15 hours of on demand. You don't even reserve 15 hours on demand you can get. But if you want to pay premium price, then you can block the time, and then that is where like our AWS managed service will come in handy. And then as a user, you don't have to interact with those hardware provider directly. You come to one shop, and then you get different modality. And if you want to pick INQ or a Rigetti, you can do that easily. So that is the beauty of the Bracket. So I was just adding to what Henri is saying. It is scarce resource. Now, apart from that, like obviously, 50 qubit. So Henri, I'm sure you're probably referring to this as a logical qubit, not like physical qubit.
But even, I mean, you also have engineering problems on top of that, such as even if you have your reserve slot for the quantum computer, then you still have potentially the networking issue where if you run the classical part far like physically far from the quantum part, then you have each time some network delays. And so you would try to run the classical part as close as possible to the quantum part, maybe. So what we would try to do if we launch an Amazon job is we would try to have a Docker image that does the classical part as close physically possible as possible to your actual quantum computers, things like this. This is very like a very involved process, which is also a reason why we want to do this instead of our clients. We try to relieve these pain points for them.
Great.
I think maybe Hamza, we can go a bit faster to the demonstration. So, okay, in this presentation, there are a lot more points that we could talk about on how our algorithm works, how we tackle noise, how we do various things. Here is a brief summary. One of these questions were asked where they asked, can we solve all differential equations? The answer is no, for sure, but we can solve already a lot. So you can see some linear equations that we can solve, non-linear, first order, second order. You can see the dimension. We are even trying to expand to 3D, but for now it's not already done. But all of these were equations that we already solved. Okay, and now I'll give the hand to Hamza to share.
What would be showing us the actual live demonstration for
Exactly.
So the idea is to show in live how we implement this algorithm and how we run it on a simple instance of differential equation. So basically the one that we showed on the graphical user interface. And so we show also how we can code with our MPQP library and how we run on rocket simulators. I think we can switch to the window I'm sharing.
And by MPQP library is like multi-platform quantum programming library for you all.
Yes.
Yes.
So
So
Thank you.
we will present it a bit more at the end because we try to follow the pipeline from the use case to the algorithm, now the implementation, and then this library at the end. So now, yeah, it's a bit the core of the demo. Yeah, I don't know if you can see my screen or not on the main stage yet, maybe. Okay.
Yeah, we can see your screen.
Great. So we'll solve this burger implicit equation, a typical simple equation in CFD, using our algorithm implemented in MPQP and triggering AWS brackets. So first, import all the tools we need, and the first step is to build together this parameterized quantum circuit. So we choose this architecture. So the goal is to first build a wall of RY gates, rotation gates, and then build this cascade of CNOTs, so control NOT gates, and repeat this schema several times. So it's like you have several layers of parameterized gates. It's the analogy of a neural network when you stack layers that depend on some weights that you have to tune. And here we see clearly the analogy. So first, what we need to do is to implement this variational quantum algorithm, quantum circuits. So I create first a circuit. So I call the class Q circuits. I have to precise the number of qubits. I don't need to precise the number of. It can also infer the number of qubits. So here it's not mandatory. It can also infer the number of classical bits needed for the measure. So this is very useful for developers. So I need to repeat this pattern for each layer, and the number of layer is called the depth. So first I'm gonna go with a for loop for each depth. So depth is integer number, so for D in range depth. Now I need first to implement this wall of RY gates. So for each qubit, I will index them. So for each qubit, I will add the RY gate to the circuit. So circuit.add, and then I can add a single gate, which is the RY gate that I imported before. This function takes all the parameters, those theta 1, 2, 3, etc. So I can use them to instantiate my RY gate. So here it will be so list of parameter. I have to take into account that we will go vertically and then jump from 1 to 6. So I add the number of qubits each time. So here it will be the index plus the number of qubits times the depth at which layer I am. So here it's D. Yeah, and I apply this qubit to the right, this gate to the right qubit. And then once I done my wall of RY gates, I have to cascade the CNOTs like this. So to do that, I can, instead of adding gate by gate, I can also add directly a list to my circuit. So I'll create a list of CNOT gates. They are contiguous, so each time it targets contiguous qubits. So I can go apply a CNOT between k and k plus 1 and make just this k vary between the first qubits and before the last one.
And Hamza, earlier
Yeah.
Henry explained and reflected a little bit upon the spectral method, but right now what you're demoing is the VQC, the variational quantum circuits, right?
Exactly. Exactly. So here I'm constructing the circuits that will give me the state that represent this function in this spectral decomposition.
Okay.
So this is the quantum part. The encoding will come later a bit when we will deal with the observables that involve this Chebyshev polynomial in the spectral approach. But here on quantum computers, especially gate-based, we run circuits. So here the first important step is indeed to build those quantum circuits. And I think I have to go number of qubits minus 1. And then once I did this, I can return the circuit. Okay, let's check if this work. I can choose a depth, let's say 2, a number of qubits 2, let's say 2 for the moment. And then I will print what's coming out my VQC function. So this function print is also using MPQP code. And so here I print, you see, I have 2 airwise, a control node, and then 2 airwise, control node, etc. And if I increase the depth, it changes. So I have more parameters. And if I increase the number of qubits, I have also a larger circuit. So this parameterized circuit will help me like get the best states that represent the potential best solution. Okay.
So your depth parameter is directly proportional to the number of qubits here?
Here, yeah, I used a parameter that just the indices 0, 1, 2, 3, 4, 5, etc. But I can have any number. I can have 0.3 here. I can have pi over 2. I can have minus 1. So the goal will be to find the best parameters. So here, just for the sake of plotting, I used indeed a list of ordered integers for parameters.
Hamza, can I send you a curveball? Would you add some barriers to make it like a tiny bit more readable?
Add some what?
Some barriers?
I can add some barriers, yes. Let me import from MPQP.
From MPQP directly.
Okay, import barrier. Let's go. So barrier is used those dash lines that used to separate elements in the circuit. So it's better for visualization. So I can add here a barrier, and I can even not put any parameter. It will infer alone the parameters. Let's see if it works quickly. Barrier is not defined because I need to import, and this should work. Wait. Wow. So you see here, it's nice plotting. Uh, so you add this barrier as an instruction. So basically in MPQP, you'll see later, you add everything. You can add gates, you can add measures, you can add noise models. Everything is done through the function add. It simplifies the programmer journey. Now we go to the equation we want to solve. So now we enter the physical problem. This is the equation we want to solve, the derivative of u with respect to t plus u, the function, times the derivative of u with respect to the variable x is equal to 0. So we'll try to satisfy this equation with two boundary conditions, one on the function itself at t equals 0. It's a linear boundary condition, as I mentioned, and the derivative of u over x at t equals 0 is equal to 1. So for that, we encode everything here as strings. The function I want to solve is u. I have what are the different orders of my function derivation order involved. I have u, so the order of derivation is 0. I have to derivate one with respect to t, so I put t, and I put x because I have another derivative with respect to x. And the variable of this function are t and x. With this will be good later to build some nice dictionaries to encode the solution. Okay, we try to optimize loss function, but indeed we evaluate this uh, differential equation at different points. So we will sample those t and x points, and for this problem we'll choose 20 points for t between 0 and 1 and 5 points for x between in the interval 0 1. So we solve this differential equation between 0 and 1. Let me just go up, and I think we have the right depth. Yeah. So I just use from NumPy linspace from 0 to 1 generate me 20 points uniformly sampled, and the same for x, so uniformly spaced. So this is the sample we will use for optimization, and for the sake of simplifying this demo, we'll also use them for validation. So after I solved, I want to compare my solution function with the classical one, so I will evaluate them both at some point, and so I will use here the same set basically. And so from this dictionary, I will then create a sample list. I can show you what it looks like. It's just a list of all possible values for x and t in this interval. So t equals 0, I have all values of x, and so on until I have 1, 1. So this is all the points on which I will evaluate my differential equation and try to have the 0 value here, the x plus 1 here, and the 1 value. So this is how it works. So here we define the points on which we will solve the problem. So this will help us generate the observables. So the observables are the physical objects that will help us to observe the state that we generated with the parameterized quantum circuit. And here we will, as Henri said, we build those observables in the way that what we observe is the value of the function at a given point. So here is the main trick of the algorithm, is that we use observable to observe a physical property of the state. The state represents the function, because as you will see, these circuits represent the function. And then if I want to evaluate it at a specific point, I give this point to the observable and have a specific observable to tell me f of x is equal to this value. So this is what we will define today. Here we have some technical specificities to the fact that we are in a PDE, so partial differential equation with many variables. So we came out with a way to split the qubits to say, okay, I want to allocate 3 qubits to the variable t and 1 qubit to the variable x. This will give me some precision on the variable, because depending on the differential equation and also on the solution, I may need more precision on one variable rather than another. So that's why here we can allocate the number of qubits we want for each variable. And so if you have a basis state I, basically the first qubit is gone because we use the trick of plus and minus Chebyshevs. But the 3 qubit here will be used for t, and the last qubit will be used for x. So if I want to evaluate my Chebyshev function of order I at t and x, it will be the product. Here we use the mathematical definition on a rectangular domain. That is the product of the two one-dimensional Chebyshev function. We have nice function that does that for us, so we will not go into detail. This is pure classical math and classical computing. We get them from SciPy. And the goal from this evaluation is to build this observable. It's diagonal observable. So it's all those Chebyshev polynomials from 0 to 2 to the n minus 1. So all the qubits except one used. And then we tensor them with z, meaning that we have all the positive Chebyshevs and then the same Chebyshevs with the negative sign. So this is what we will build here together. So first, let's build the diagonal elements. So those diagonal elements, diagonal elements, they are just, I will create a list. They are just all those Chebyshevs from I equals 0 to 2 to the n minus 1. So it will be, I will use Cheb multi-dimensional. So I give the point here on which I want to evaluate Tx. It's a two-dimensional point. I give, okay, I will have an index, and my index will be here in range of 2 to the number of qubit minus 1. The number of qubit here will be given by the number of allocated qubit plus 1, this I0 qubit. So 3 plus 1 plus 1, meaning that for this demo we will use 5 qubits to solve this equation. So I can put 2 to the 5, but more generally, if someone wants to play after, it's just the sum of a number of qubits, and this the sum of all the qubit allocation here.
And should it have the -1 or not?
No, because it's already -1 with this qubit is sacrificed
Okay.
more or less, so already have -1 here, so it's it's all good. And then after the index, we give the number of qubits, the general number of qubits. So it's defined above, it's 5. And here we give the derivation orders, telling me which do I have a derivation of this Chebyshev or not, and this will compute for me all those diagonal elements. Hopla. And then from those diagonal elements, I can even define as NP array. I construct, yeah, I can construct now. I can do the plus and minus 1 trick. So I will use np concatenate. Concatenate. I will take the diagonal elements and then concatenate the minus diagonal elements, and then I will return my observable. So all those are my diagonal elements of the matrix. If you remember, you have the matrix is a lot of zeros and diagonal elements are Chebyshev polynomials. Here I will use the JAG function to construct this diagonal matrix from those diagonal elements that we just constructed here. I think we're good. So this will help us to evaluate the function at some points. So this is very important. We have a function encoded in the circuit. We have observables, so we can evaluate the function, and I can play with the parameters to have the best evaluation of the functions. And so here I need to construct observables, so I will need to evaluate the function at some points. So basically I will need to evaluate, if I go back to the equation, I need to evaluate the derivative of u at some point, the u and the derivative of u with respect to x. So let's encode this in all the observables. Let's generate them. So diagonal observable. So for all the samples we have in the sample list, I give the point to the diagonal observable. So here is the sample. So the point xt. I give the qubit allocation. So we said 3 qubits for t, 1 qubit for x. And I give the order of derivative. So here I want to evaluate u. So no derivative. So this is for u. So I generated all the observables for all the sample points to evaluate the function ut. and then I can add the derivatives. So I will do the same, just change the derivation order. So here we are building all the physical elements we need, the quantum parts we need, but we do it on a classical way. So then when we will submit the run on the quantum computer on the simulator, everything is ready. So we are encoding here the problem. Diagonal observable. So we generated our observables, which is not defined, probably. Let's run this and then let's run this. Object of type int has no length. Okay, because here maybe I put where is it?
And you are running all this in the from the MPQP library, Hamza?
Yes. So we will see later when we will execute the circuits. We will so here this observable is indeed an object from MPQP, and then we will run on bracket devices through MPQP. Yes. Let me understand here. What is the error exactly? Observables. Object of type int has no length. Okay, I think it's this. I have to give the qubit allocation here. Okay, I think I need to get can I convert it to what's going on here? The joys of the live demo. For index in range of this. Let me check in the check multi. I think
range. Can you show me again the range? Sum qubit. Okay, now this should be good.
it's appearing apparently.
So it's the diagonal elements.
Yeah. He's not happy with those elements. He can
Does that help if I relay a message that it needs to be a list?
elements is not defined. Okay, we can print them here. Maybe. Oh, okay. We opera and then.
It's a function.
No, because it's the wrong one, of course. Right, it's a list of diagonal elements, and they should be able to concatenate them. I don't understand why. Okay, okay, it's not a problem. I have some backup notebook on which I'm sure it will work, and on which we do the same. And we will we'll just explain what's happening. Okay. So let's rerun everything and we continue at where we stopped. Okay, we define everything, define the sample, the observables, and we define the expectation measure. Okay. Here we define the function. We need 5 qubit and depth of 3. Okay. So now we need to initialize the parameters, and maybe you saw quickly a slide from Henri, but a very important part of the VQA is to have a very good initialization. If you initialize your angles very far from the solution, you may not converge, and because it's a hard optimization problem, you have many phenomena, barren plateaus, etc. So having a smart initialization strategy is very important. Here we do not show the smart intelligence strategy that we develop in R&D team, but I use a random seed to start not close to the solution, but somewhere where I know it will converge. And later, if we have time, we can play with this random initialization to see if it converges well or not. So the number of parameter is the number of parameter of the circuit plus a scaling factor that is used to amplify or not the value of the function because it's quite bounded. So here we generate random uniform parameters, angles from 0 to 2 pi. Okay, now I need to encode my function and I need to encode my differential equation. So I recall the differential equation. Maybe I go a bit down. So I have my loss function. This is what I want to optimize. I have a loss that tells me what the error on the differential equation. I have a loss that tells me what's the error on the boundary condition. And then I have a final loss that combines them both. Okay. So this is the set of equations. So let's start with the boundary condition. I want that my value, function at 0 is equal to x plus 1, and then my derivative at 0 is equal to x plus 1. So this is what we do here. We get all the values of u at t equals 0. This is what we do. And the value of u derivated by x at t equals 0. And then we compute the error. So this is the error for u at 0 should be equal to x plus 1, and the derivative should be equal to 1. And so then we use what Henri said, the mean squared error. So those are vectors. We compute the dot product of these vectors. We'll multiply them and do the sum of the squares, and we divide by all the samples. And this will give me the error I commit on the boundary condition. In the same spirit, here I encode the error I do on the differential equation. So you see the derivative of du and dt, derivative of du so this is u because there is no derivation, and then derivation of u with respect to x. So this is exactly my differential equation. It should be equal to 0, so this is what I want to minimize. We call it the residual. And I also do the mean square error, and I return the results. Okay, so let me define those functions. And then we go to the real loss function, and this is where the quantum and the classical part is happening. I define a number of iteration, and I use a counter iteration to have nice displays of the run. You will see later. The loss function takes the parameter of the circuits. I get the scaling vector aside and the parameter of the circuit, and I use it to define a circuit using my VQC I defined earlier. I add an expectation measure with all those observables. So here I'm telling I want this circuit and I want all those measures, and the magic appear here is I run this circuit on AWS here bracket local simulator, but indeed I can choose all the devices available on AWS brackets. So I can use the density matrix simulator, the SV state vector. I can use IonQ backends. IQM is 20 qubits backend from IQM, QERA, and as well as Rigetti. So those are all the available devices that are supported in MPQP. And so with the same function, basically, this is the advantage of having MPQP on top of AWS. You define your circuits, and with the same function or the same measures, you can basically switch from local simulator to remote simulator to remote quantum computers. And so all the difficulty of dealing with the different stuff is hidden here for the user. So I'll use the bracket simulator. I will run and I will get the result. The result will be the list of all the expectation values, meaning all the evaluation of the functions. And I will use them here to put, I will put them in some dictionary, the value of the function at this derivative. We have all the lists, etc. So here I construct all the lists that just split the result basically. I compute the loss on the boundary condition and the loss on the differential equation from those results. And then I combine them. It's a linear combination. You can here tweak the coefficients in front of each part of the loss, and this is what we call loss balancing. It can be quite difficult task from maybe emphasize the error on the DE or on the boundary condition depending on the problem.
Mhm.
Usually we prefer to emphasize the loss on the boundary condition that guide us to the solution that is really unique for this boundary condition. Okay, so here we have all the ingredients we need to start run our optimization. What we can do is okay, so we use SciPy minimize. We can also use MPQP minimizing tools. So I give to my minimizer the loss function, encoding all these differential equation, initial parameters, the optimizer. You can use all the optimizers from SciPy optimize. You can also in MPQP introduce your own custom optimizers, and I give a maximum number of iteration, and then we let it run. Okay, so it will take
Maybe you
several.
can carry on the explanation while it runs.
Yeah. So after it, so what we will get out of this minimization is basically a set of angles, and optimal angles. As Henri said, we iterate until we have those optimal angles. After we have the optimal angles, we can reconstruct the circuits, and this will give me my solution. So this is what we do later in this result class. That's unpackage everything you need. Everything you need to like decode the results. So this is what you see also on the graphical user interface. You don't get those quantum results. You just have to deal with the real value, the real plots. This is done for you using this result class. You give the solution vectors, you give the depth of the circuit, number of qubits, all those observables, the sample list, the function you want, the solution function. So here the solution function is this what we should obtain. This is the theoretical solution for this differential equation, because here, okay, it can be solved analytically in this small example. The samples on which you want to validate, and the equation, etc., and then you can plot the results.
And,
Uh,
and Hamza, this is the detailed decoding derivation of that main equation which you showed us initially with the error balancing and original one,
yes,
right? Okay.
yeah, exactly. So yeah, so at the end we'll get some results, and okay, apparently there is some problem on the oh, okay. I think since we are a bit short on time, uh, so you see that here we have the global loss that is decreasing. It started at 73. You have the loss on the differential equation that gives you how well I fit the differential equation. And here, how well I fit the boundary condition. You see that it's a bit better because we emphasized it in this uh, loss balancing, and it will continue to decrease. We can look at this solution already. I think it's not bad 0.3, but we can go further. I think here I have CPU problems with the streaming, etc. So I think I'm gonna use pre-computed result to show you what it would look like. So this is
And
what
what
we
is that
should.
percentage value there? Is like how much it has processed so far?
Yeah. So exactly. So I said 60 iteration in total. So this gives me, yeah, how far we are in this optimization process. Doesn't tell me how good is the result, because sometimes at the end we can have the good result can appear only at the end.
Mhm.
Uh, but yeah, so let me enter those. So these are the parameters we should obtain after the end of the simulation. So this is the scaling factor telling me how for I multiply the function by this scaling factor, and all the other are angles. So basically here it's almost pi, and here is almost 0. So telling me, okay, this rotation has more impact or not. And then from those angles, we can rebuild the solution. So we use the result class. It will show me the plots actually of the comparison between classical and quantum. So here we have
Nice.
a 3D plot of the results. So of this Berger equation. We don't see clearly here, but there is, you have a blue and a purple curve overlapping. They are quite on top of each other. So this is because the result is quite good indeed. And you can see that if you cut by some specific value of t and x, you can see that here also. So in green, in blue, you have the prediction, the classical one, and
Okay.
in red you have
Real one.
the one, yeah, the real one. No, so in blue the prediction by quantum, and in red the classical one. So you
Yeah,
see here some small variations, not perfect. So to have more precision, you can improve the initialization, run more iteration, or have more qubits, basically.
great.
So yeah, that's it for the technical part. Uh,
Nice. So one strategic question, right? Like I think we are running short of time, but now if a user like me or from the audience who wants to probably experiment with this, or what we call at AWS like call to action, right? Like what they should
yes.
do after hearing today live, and then if they watch recording, how they should get in touch with you, and then
I think they can contact us directly. We can prepare for them a demo of what we have in detail, and then we
Mhm.
can discuss how we can collaborate to add use cases on this platform. So the online platform is not yet open to the public. We are working hard to make it accessible for the public. So when we will be open, people can play with the parameter, the equation, and see those equations solved directly on the platform. They can also contact us so we can work together on the
Great.
implementation of the algorithm. The algorithm is under patent pending, so you need a license to use it, but we can collaborate together to execute it on a quantum computer or to solve your specific equations. And what people can do also is download our library MPQP and start to use it, so they can leverage the power of quantum computing and also have direct access to all the AWS bracket devices.
Great.
Maybe
I
I'll let
would like
Henri. Yeah, go
I
ahead.
would like to ask about that. How does this MPQP library or aligns with your broader mission of making quantum computing accessible and platform
Yes.
agnostic? Yeah, like what are the
I,
benefits? Yeah, how does it
Maybe
align?
if we have the time, I can show you like 2 slides
yes.
very briefly that explains the positioning of MPQP. Because a notable fact for MPQP is that so you can share my screen if you can see it. A notable fact about MPQP is that it doesn't require you at all to specifically want to solve differential equations, something like this. It's really a tool for anyone who wants to try quantum. The goal is to be as easy as possible to use.
Great.
So it's basically an in-between layers between a user and the various libraries that exist. So the reason why we created it is that we really felt this pain point of having to recode each time our algorithm, each time we wanted to try a new platform. But also we noticed that there were like inconsistencies in a given platform. So this is a way for us to give back to the community by providing a platform that fixes the bugs that we notice. We of course also participate directly to the libraries when we can, when they are open source. We provide this, we write the issues, we provide some suggestions of modifications, and MPQP is in this spirit of having an open and friendly community around quantum. Yeah,
Great.
so
Great. Yeah. So I think
um,
we are coming to end, Henri, Hamza. I
yeah,
think I'm sure, like we can go for another 2 hour, and it's pretty much getting late for you guys too in the Paris. But I think like, our time spent here, 2 hours, just went like explanation of and all, right? But
yeah,
we are very grateful
No,
to you
great
guys
person.
and Laurent, right? Like
yeah,
to share their wisdom and knowledge and what this can do for the future work.
yeah.
Any
Thank you for
parting
your
words
time.
you have for the audience?
If you want to contact us, here is some resources. So you can
Nice.
contact us either on our Discord, GitHub, whatever. We are very open to work with you, be it with academics, agro providers, industrial partners, investors. we are looking forward to have some contact with you guys, and thank you AWS for the opportunity of talking on your platform. It was a very nice chat that we had. Super casual, super friendly. Yeah, thank you so much.
Looking forward to getting more interaction, and thank you so much, everyone. Wonderful presentation, and thank you so much, all the audience who are continued with us. Don't forget to give us your feedback, and you let us know if you want to reach out to ColibriTD and these brilliant gentlemen. With that, take a nice break and have a good weekend, you all.
Thank you.
Thanks,
Bye, everyone. Bye.
And good night for the Europeans.
Good night.
Absolutely.